What's up, what's up, what's up? Today we're going to be evaluating this crazy integral, the improper integral of sine x over x dx. Now you look at this function, you're like, what do I do here, you know? It's like, it looks like a dead end, essentially. This is one of the most important expressions in all of calculus, and it's very likely that you probably get this asked at a plumbing job that you're applying for. So to start, essentially we're going to be evaluating this integral using the Feynman trick of integration. So what that is basically we want to rewrite this integral as I'm going to call it I of t. Why not? And I of t is just the same integral that we have with our new parameter. Simple, right? It's a really powerful trick because now what we want to do is we want to differentiate under the integral sign. So we're going to have our new function or a differentiated function, I prime of t. And this is just the same thing, exact same thing. And we have the partial derivative with respect to t here. Now, taking the partial derivative of this is as simple as it is just the integral of improper integral, and then we have the negative x e to the negative tx, since it's with respect to t, x is a constant here, and it's just sine x over x dx. Woohoo, we get rid of that x that was bugging us at the beginning. If only the expression could be the integral of sine x. So now we have our new expression, which is the improper integral of negative e to negative tx sine x dx. Problem solved, we can evaluate it, right? Not exactly. Now we have to use, I guess, the formula that we have for integration by parts. So that's, I guess, this formula that I'm going to show you. And we're going to denote our e to the negative tx as our u value, and this will be our v value. dv, sorry. Essentially, this is equal to, by integration by parts, negative e, negative tx, times cosine x, the derivative of sine x, from 0 to infinity, our boundaries of integration, and we add the improper integral of te, negative tx, cosine x dx, negative t, sorry. Now we want to clean up this expression a bit, so we're going to evaluate the limits of this. So the limit as the expression approaches infinity, as you can see, it is just a negative exponential. We can take out the constant term as a negative exponential approaches infinity. This x value approaches infinity, it will equal 0. And then to evaluate the limit as x approaches 0, again, the constant term is taken out. So anything to the power of 0 is 0, and cosine of 0, sorry, anything to the power of 0 is 1, and cosine of 0 is also 1, so we get 1. We've taken out our constant, which is minus 1, so we just get that the expression above is minus 1 plus this integral here, and that is just the integral 0 to infinity minus te minus tx cosine x dx. Okay, cool. We're in the same place as we started. We're going to do another integration by parts to get this back to a sine x. So again, u, again, dv. Same old, right? So essentially, this is just minus 1. And we add the new expression, te minus tx, and then sine x. Since the negative from the derivative here and negative here cancel out. And that, again, we have to evaluate that from 0 to infinity. And we add it to integral from 0 to infinity of t squared, negative cancels out, e to the minus tx sine x dx. Cool. So now we have to go back through this entire process of evaluating the boundaries of integration again, but we're going to do it much quicker now. It's a pretty simple one. We said that as x approaches 0, infinity, sorry, the function will approach 0. We have a negative exponential here. And then even though for 0 this is 1, sine of 0 is 0, so we get that this entire term cancels out. And we just get it is minus 1 plus the improper integral t squared e to the minus tx sine x dx. Now, t squared here is just a constant. We know that it's a variable that we introduced, but in terms of this integral, it's just a constant because we are integrating with respect to x as our variable of integration. Minus 1 plus t squared integral 0 to infinity e to the minus tx sine x. Now, if you have good memory and you haven't fallen asleep yet, you'll remember that this is the very same expression I dash t, and we have been working with I dash t all this time, so we can rewrite this expression. Since we lost the minus that was here originally, we're going to replace this plus with a minus. So I dash t equals negative 1 minus t squared times I dash t. We want to essentially collect like terms now, so we get that I dash t minus t squared I dash t is equal to minus 1. We factor out I dash t and we divide it by what we get, which is 1 minus t squared. So we get that if we divide I dash t is equal to minus 1, sorry, this is a plus t squared. Now, if you know your standard results, you'll know that this is actually just the negative arctan of t. So we're going to just write it as that I dash t, or sorry, just I of t now, since we are integrating the function. I of t is equal to negative arctan t, and we can't forget our constant of integration. Okay, so what now? We're going to compare this arctan t to our original expression I of t. So what we're going to do is we're going to just rewrite the entire expression as we had it. And we're going to have it as, sorry, negative arctan t plus c is actually just equal to the improper integral that we had at the beginning. E to the minus tx sine x over x dx. Perfect, right? Now, you may be wondering, what is c in this case? And we're going to find that out we're going to evaluate the limits as the variable t approaches infinity on both sides to find out. So, as this negative arctan t plus c, to find the limit as t approaches infinity. Now, if you look at the arctan function, as t approaches infinity in this case, or I guess on a graph x approaches infinity, the arctan function approaches value pi over 2, half of pi. Pretty standard. Now, to evaluate the other limit of the integral on the right, all of this doesn't matter to us. Essentially, what matters to us is that we have a negative exponential here. We know that in any case, as t approaches 0, this entire expression here will approach 0. So we get that this limit is just 0. Therefore, our constant of integration, or I guess the evaluation of this integral from 0 to infinity, is just equal to pi over 2. It's It's a pretty crazy result for what we get. I mean, it's a very big integral, and to get such a nice answer at the end is kind of unexpected. So I hope you enjoyed. I hope my explanation makes sense. This is a really powerful integration technique that I hope you guys can master and maybe use in your driving test next year. Thank you.